Okay, welcome to the second part of the lecture, the second lecture on language. And in this part, we will speak about the cohort theory and the trace model. Okay, so let's start with the cohort theory, which has been proposed by William Marston Wilson in the 1980s. And this is a very cognitive model and explains how visual or auditory input, so it holds for both, of words is mapped onto a word in the listener's lexicon. So our lexicon is our long-term memory, so to say, of all the words we know. And when we hear or read something, we have to decide which word is it in our lexicon. So there has to be an identification and mapping onto that. And the cohort theory explains this process. And one of the key propositions is that the processing of the input of the word we hear or read starts with the first phoneme and not only after we have heard or read the whole word. So we do it directly. And this observation is supported or the idea comes from shadowing experiments. Because if you remember our attention lecture, shadowing means you have an input over headphones and you have to speak out what you hear while you hear it, like these simultaneous translation people at the UN or something like that. And people start shadowing the words before they have ended. So they already processed the start of the word. Let's go through an example. And the prior context might be, I took the car for a, and now you hear the phoneme s. So it could be that you now will hear soap, spinach, psychologist, spin, sun, spank, a lot of things. And this is called the initial cohort. And all these words are activated in our lexicon. If you remember the very first lecture, we spoke about these semantic networks with the spreading activation, where when one node is activated, and I think we had this concept of animal or fish, which is activated and then it spreads through this network with some time. Then we may hear the phoneme p, so it's sp. So we can exclude words from our cohort. So it can't be soap anymore, it can't be sun anymore. And this goes on. Then we hear I, so it could be spin or spit, and then n, spin, and it will be clear, oh yes, that's the word we are looking for. I took the car for a spin. And the point where we have identified the word and said, that's the word we choose from our lexicon, there are no other alternatives left, this is called the recognition point. That's the only word left in the cohort. And that doesn't always need to be the last phoneme or letter in the word, because some words are so unambiguous in a way that the recognition point might be earlier already. So after the recognition, the word is selected from the lexicon and integrated into the context, into the sentence for semantic, syntactical processing. And it's suggested that the processing, the type or nature of processing differs. And that early in the processing, when we just take the phonemes and try to reduce the cohort, so before the recognition point, the processing is mainly bottom-up, driven by the input. While later in the processing, when we've narrowed down or at or after the recognition point, it's also influenced by top-down things like the surrounding sentence and information which we have. That's all I want to say for the cohort theory. And now let's go to the trace model, which in a way is quite similar to the cohort theory. There's quite a bit of overlap. And the trace model has been proposed by McClelland and Ellman in the 1980s. And it's a computer model, a connectionist model, and I think it will be quite a good of an illustration to go through that model to see how we can do that. So, as I said, it shares some similarities with the cohort theory, like selecting the word along a time course. And this is now a graph about the activity of different words in this trace model when different input is received. And this looks pretty much like the cohort model would predict as well. In the beginning, all words, like the green one is Bill, the yellow one is bat, the red one is the activation for ball, and the blue one is bald, and this is the one which is then finally selected. So here we have time. This is probably just steps in the computer model, iterations. And this is the activity level of these words, and if the activity level surpasses a certain threshold, then usually the word is selected, or after a certain time you pick the one with the highest activity. Now they all start with B, so they all start after a 0 activation level on the same way. And then the A phoneme comes in, and you see that Bill loses activations because there's no A, but the other words continue. Then we have bad, which pretty soon as well differs, and then we can ball. They say pretty much the same, and then the D comes in the end, and ball fades out, and bald is the winner of that. And in this part, I hope it will become clear how computer models, connectionist computer models, can be used to model cognition, and how they can be used to get insights in cognition, because we will go through that in a little bit more detail. So that's the whole trace model in a glance, and the idea is to have different levels or layers for the auditory features, for the phonemes, and for the words. So this is the lowest level and this is the highest level, and that there are connections between these different levels. So the phoneme level can activate features in the auditory level, and of course the auditory level can activate this, and the phonemes can activate words, but the word level can also send back activation to phonemes. What is important to note, and an important feature of this model, is what is called lateral inhibition. So within a level, these different elements will inhibit each other. So if this phoneme is active, it will inhibit the other phonemes. And if this is active, it will inhibit the other phonemes. Let's have a look at these layers a little bit slower, step by step. So the auditory features, and the trace model is set up by a simplified spectrogram, which tries to read and identify the place and manner of articulation. So it looks a little bit like this for the word bag, and just energy frequencies like that. So they try to mimic what we know about real life speech perception. Then we have the layer of phonemes, and what they suggest is that we have a complete set of phonemes for each letter in a word. So if a word has 6 letters, then we have 6 complete sets of phonemes. In terms of letters, you would say A to Z. And as I said before, the phonemes within a set inhibit each other. And there's this winner-takes-all principle, so that only one phoneme in each set is identified. This may look like this. So we may have all the letters here in the alphabet for the first phoneme, the second phoneme, and the third phoneme. So we would have cat here. Note that I know just use standard letters to describe that, but the model is for phonemes actually, so it's the word cat would be like that. And then we finally have the word level, and this word level reflects the lexicon which we spoke about in the cohort theory, so all known words we have. And in trace, this lexicon is limited to 1-syllable words, so rather short words. And again we have this lateral inhibition, so that only one word is selected and we don't end up with like 2 or 3 similar sounding words, and we are left with an ambiguous interpretation of the situation. These words are activated by the phoneme layer in a bottom-up fashion. And the words which receive activation from the phonemes feed some of that activation back to the phoneme layer. So again, this idea of semantic networks in a top-down fashion. So the model tries to integrate both bottom-up and top-down processing. And such models, in a computerized way, they work in cycles. So the activation spreads through the network step by step. And let's have a look at an example, the recognition of the word cat. The auditory features, first we have the phoneme k in cat, and then we have the phoneme layer. So this is the auditory features here. We have this phoneme, and it can be described by the place and manner of articulation in form of a simplified spectrogram. Then we have the phoneme layer, and the k sound on the first position activates the phoneme for k. Now, like in the predicted by the cohort theory, hearing the k would activate in the word layer all words which start with k. So, for instance, cat, can, cop, and more words. Remember, it's just single syllable words. Now, we said we have top-down influences back, so the word layer now activates phonemes, the related ones. So when cat is activated, the activation is spreading again back to the phonemes. Of course, these effects become weaker, so that what is fed back is weaker than this is what is forwarded. And having cat been activated would say, okay, the second phoneme then should be A, and the third one should be T. Can is activated, so the activation spreading back activates the C, the K, then the A as well, but then as a third phoneme, the N sound. And the same for cop, C-O-P. So these phonemes are now already slightly pre-activated from this top-down feedback information. Now I hear the A sound of cat. So my analyzer says, okay, the second phoneme is actually the A. And now I can remove cop from my cohort. And when I remove cop, let me go back, then I also remove the top-down pre-activation of the O and the P on the phoneme level. So it's thinning out, it's pruned out a little bit. Then I hear the T sound as a third letter, and I can remove can from my cohort, so that only cat is left over as the final word, and I can select that word and from my lexicon and do then the further syntactical processing. Okay, I hope that clarified how such models can be used to simulate how the speech perception might work. The model has a couple of strengths. And the first one is, it's a computer model, so it's very well specified. You have to program everything, you have to set every parameter, or if you don't have to set it, if it can be learned, then you can read out every parameter and can manipulate it and see how the model behaves. Is it mimicking human performance or not with this certain set of parameters? It nicely explains how the bottom-up and top-down processes interact. And it can explain a number of empirical findings, and that's something we always try to see in a computer model, that we can simulate and explain the data we get from human participants. So, for instance, the categorical speech perception we had in part 1. Just as a very quick reminder, when we have two phonemes like da and ta, and we gradually morph them towards each other with a speech synthesizer, then we have this categorical perception. So in all in-between stages, we also hear either a da or a ta, but never the sound in between. The trace model explains this by the winner-takes-all principle. And if you remember, on the phoneme layer, we have this lateral inhibition. So the phonemes inhibit each other so that there can be only one winner. When we would hear something in between, and we only have a representation for da and ta, we would expect something like da and ta are both activated so that we perceive a mixture of both, but only one can be activated. Another finding which can be explained is the word superiority effect. And if you remember, in the last lecture, Language 1, we spoke about this in the visual domain, when people had to identify a letter presented to them, and the presentation was so brief and masked that it's really difficult. And it's easier to identify the letter when it's part of a word as when it's on its own or part of a non-word. The same happens in the auditory domain. So the task is, when you listen to a word, listen to an auditory stream, to detect a specific target phoneme. Could be an a, t, a b, whatever. And this phoneme could, in one condition, occur in a sequence of phonemes which form a real word, or in another condition, in a sequence which form a non-word. And what you find is that the detection is faster in this word condition, when it's a real word, as compared to a non-word. So how can the trace model explain that finding? It can be explained by the top-down effect, by the feedback of the word layer back to the phoneme layer. If you remember that all pre-activated words activated the phonemes of these words, already the ones which are expected. However, if we have a non-word, then we don't have any activity in the word layer which could feed back onto the phoneme layer. So that is missing, and this activation, which is spreading back, helps in identifying the right phoneme. But of course, as usual, there are weaknesses of the model. And as I already said a couple of times, the vocabulary is limited to one-syllable words. The crucial point is that there are certain considerations which say that it's really unclear and actually questionable whether it would actually generalize to larger lexicons and longer words. So there are certain limitations in the concept of the model, of this type of models, which may doubt that. So it's not simply say, like, yeah, just program a little bit more and then it will naturally go to 2 or 3 syllable words. There may actually problems be coming up. There is no learning implemented in the model, and the whole lexicon and how the connections are set up by the experimenter. That is not saying that it's not possible, but we don't know yet because it hasn't been implemented. And the top-down effects which we discussed are sometimes overemphasized. And you may say, well, yeah, then just turn down the parameters or something, but then what happens then is that you may suddenly lose some other effects you can explain, which you suddenly can't explain anymore. So this needs a little bit more fine-tuning. Okay, so just a quick summary. The theories of speech recognition we talked about. We had the motor theory of speech recognition by Lieberman, where the idea is that to recognize speech, we covertly perform the motor act ourselves, which we would need to do to produce what we have heard. And by saying, okay, because I had to produce that phoneme, the other person must have said that phoneme. We have the cohort theory, where we start with a large cohort and then gradually reduce that until the recognition point where we have the final word selected. And we have the trace model, which is a connectionist computer model and simulation, which nicely integrates these bottom-up and top-down processes. If you have questions, please post them on the BBL, the relevant BBL discussion board. And thanks a lot for listening, and maybe see you back for the third and last part.